we need to look at intermolecular forces because that's telling us how attracted are these and how much energy do we have to put in to pull these apart from each other. All right, these three molecules, okay? So we're going to look at these three, and we are going to first compare which one has the strongest intermolecular forces. And then we are going to decide which one then probably has the highest melting point. All right. And you might be saying, why are you asking me about melting point? And we will get to that in a minute. But we want to think about everything we've just talked about, all the intermolecular forces that are possible here. And then what we want to look at in terms of comparing these, which ones will have the strongest intermolecular forces. Okay. So first we can look at these and we can assess, are the molecular weights similar to each other? Okay. And yes, they are. Okay. True. Oxygen has a slightly larger mass than a carbon does. Okay. Here's a carbon in this spot, but it's not so much that would explain everything. So we want to look at really roughly, do they have somewhat similar mass? And it's true. Okay. So they all have similar molecular, you can say mass, you can say weight, one of those. Molecular weight's more old school, but they've got similar molecular mass. Okay, what about structure? Okay, remember when we talked about the long chain versus the branched alkane and the differences in structure? We used that to explain the differences in intermolecular forces. Well, what do we see here? Boom, boom, boom. These are all very similar in their structures. So we say, all right, similar structure. That's not going to help us then. Okay, so now we can look at what are these different atoms and what kinds of molecular forces are going to be relevant for each one of these molecules. All right, so let's start with this one over here because this is all carbons and hydrogens. This is line angle drawings is what we're looking at here, where each end of a line, it's implied that it's a carbon and that the carbon has enough hydrogen so that it has its octet. And so anywhere where there's this vertex, there's also a carbon there. So we've got 1, 2, 3, 4, 5 carbons here. All right. And I'm surrounded by hydrogens. All right. And so what that means is anything that's just carbon and hydrogen, we can say reliably that this is a non-polar molecule. And when you've got a non-polar molecule, that means you're only going to have London dispersion forces. Okay. So London, I usually just say London forces, but a lot of people use dispersion. So I'm going to put both of those terms here. London dispersion as just kind of two names for one thing. Okay. Now, pro tip, all molecules have London dispersion forces. So we can actually add in and say, well, hey, so does this one. It's got London dispersion forces that are relevant because it's a molecule. It's got electrons that can move around. And same with this one, London dispersion. Okay. But for this molecule, this is it. This is the only relevant intermolecular force. Okay. What about this first one here? We've got an oxygen. Oxygen is quite electronegative, isn't it? All right. And so that means it is going to be pulling electron density away from this carbon that's right there. Okay. So this is creating a dipole. This will be slightly negative here, the oxygen, that electronegative oxygen. And this carbon here is going to be slightly positive. Okay. So we can say that, yes, it is expected that this molecule is going to have some dipole-dipole interactions that will be relevant. Dipole-dipole. All right. Let's look at this molecule. We've got, once again, we've got this electronegative oxygen, and that is bonded to this carbon here. It's also bonded to a less electronegative hydrogen. Okay, so along with our London dispersion forces, we would also expect that we are going to have a partial negative charge near this oxygen that's electronegative, and that we will also have partial positive. That's more, and I'm just kind of drawing it over here. That's more, I have the hydrogen over here, carbons over here. Okay. So dipole-dipole is relevant, right? Which leaves us with what other intermolecular force might be relevant here. Okay, what do we see? We've got oxygen that is bonded to a hydrogen. Whenever we see that, that is our indicator that hydrogen bonding is happening. Whenever you see hydrogen that is bonded to one of those super electronegative atoms like fluorine, oxygen, or nitrogen, you can confidently say that there is going to be hydrogen bonding that's relevant. Okay, so we can also include hydrogen bonding to our list. And ultimately, this allows us to assess each one of the relevant intermolecular forces for each one of these molecules and decide which one has the strongest intermolecular forces, which one has the weakest. Okay, so this molecule has just one intermolecular force, London dispersion. This molecule, it's got these three. And this one has the two. All right, I think we can do this, right? Okay. The one with just one, this one will have the weakest intermolecular forces. And this one here, the strongest. It's got all three of those. Okay, and then what? Okay. So I had mentioned that we can talk about melting points and also boiling points as well. So let's do that in the context of what we just did, what we just compared and just learned about. All right. So what does this mean if we have melting or boiling points? What are we doing? What are we doing when we're melting something or we are boiling something? Okay. If we are melting it, that means we are going from the solid phase to the liquid phase. If we are boiling it, that means we are going from the liquid phase to the gas phase. And that means that we are actually just we're not changing anything chemically. We are doing what is called a physical change. All right. And so with a physical change, it's like, hey, if you have these two pentane molecules and maybe let's make them the same so we can compare and say, hey, we've got pentane. Okay, here's two pentanes. So let's say we have this solution that just has pentane in it. So that means there's only going to be just a bunch of pure pentane molecules, and they're all just like hanging out together and they're attracting each other in the way that they do and all of this. Okay, and so let's imagine that this is in the liquid phase. So liquid phase, they're just swimming around, right? Okay, and then we heat them up to the point where it boils and it becomes a gas. And what are we doing there? When we're melting it, we are actually breaking the intermolecular forces. We are breaking that attraction that is between the two molecules, and we are separating them. And remember, now look at me here. Okay, gas phase, Liquid phase, they're close together. Gas phase, they're so far apart. Okay. So these molecules, I can't even fit them on the screen and have it be relevant. Okay. They're very far apart when they're gases. And so what that means is we need to look at intermolecular forces, because that's telling us how attracted are these and how much energy do we have to put in to pull these apart from each other. And if we have to put in a lot of energy to pull these apart from each other, then that means we have to bring the temperature up a lot. If this interaction is weak, no problem. Cold temperature, they'll just be like, pop apart. No problem. If they're strong, though, we've got to bring up the temperature. We need to add more heat. We need to add more energy and finally get these moving around and then break those bonds and put them into the gas phase. Okay. So these melting points, boiling points are higher. Okay. So I'll put higher melting point, boiling point. MP, BP are pretty standard abbreviations for that. Higher melting points, boiling points with stronger intermolecular forces. Okay, so we're going to see this direct correlation. So given that, hey, if we look at these molecules that we've got up here that we investigated and we assessed what are the intermolecular forces that are relevant here, then we can say with great certainty which one of these will have the lowest boiling point, or in other words, the weakest intermolecular forces that are very easy to break, so we can do it at cool temperatures and put it in order all the way up to the molecule with the strongest intermolecular forces, the molecule that is tightly held together, the molecule where we have to put in a lot of energy, high temperatures, in order to break those molecules apart. We need to increase the temperature, which means we are increasing the melting point, boiling point. Okay. So in terms of melting point, boiling point, let's put these in order. Let's see. Do we want to put, let's put low to high. Low, melting point, boiling point. And those always go together, by the way. The melting point, boiling point. If one's going up, the other one's going up. So we'll put these in order from low to high. Melting point, boiling point. And these go hand in hand with, let me move this up, weak intermolecular forces, weaker IMFs, stronger IMFs. Okay, so which one of these was the weakest? That was our molecule with just carbons and hydrogens. And then in the middle, we had our molecule that had a dipole, but it didn't have the hydrogen bonding like we have over here. Okay, there's our molecule with the hydrogen bonds. Okay, I'm going to circle them so you can kind of see them a little bit better. I also did them in green so you can hopefully see them. Okay. All right, we put them in order. We assessed the intermolecular forces. We then tied it in with melting points, boiling points. This is super relevant for separating out different kinds of oils and gases. This is very relevant to fossil fuel production and separating them out. This is all about intermolecular forces, physical changes. Distillation is relevant to all of that. A lot of separation science brings in these ideas of intermolecular forces. So these come into our lives in so many ways in industry, and then also, honestly, just our life. Our proteins are held together in very specific configurations with hydrogen bonding. Our DNA is held together in a very specific way with hydrogen bonding. There are also, I didn't talk about ion dipole interactions, but that's also another significant one. Okay, so our DNA there's ions that are floating around that are helping with the structure there. And the list goes on and on of how this is relevant in everyday life. So some of it's industry, some of it is biochemistry, some of it is organic chemistry, some of it is inorganic chemistry. It's everywhere.